All right, welcome back to AI Paper Podcasts. This is the YouTube series where we really get into the weeds on the latest AI research.
That's right.
Today, we're diving into a paper called PTMark, Invisible Watermarking for Text-to-Image Diffusion Models via Semantic-aware Pivotal Tuning.
Quite a mouthful.
It is, but the core idea is pretty crucial. Basically, you know how AI image generators are everywhere now?
Oh, yeah, exploding.
Well, watermarking them to show they're AI-generated or protect copyright often messes up the image itself. It changes the meaning, the look.
That semantic drift problem, yeah.
Yeah.
It's a real headache.
Exactly. So this paper, PTMark, introduces a new way to embed these invisible watermarks without that semantic damage. They claim it preserves the image's meaning much better.
And the numbers look good, right? Like a 10% boost in semantic accuracy metrics.
Yeah, something like that. And also, get this, 4 times more efficient than some of the other top methods out there.
Okay, that's definitely worth digging into.
Yeah.
Efficiency is always key.
So, for all you researchers and engineers tuning in, we're going to unpack how PTMark actually works and why it might be a big deal. Let's get into it.
Sounds good. And it's timely, because as these text-to-image models get better and more integrated into creative workflows, well, copyright and provenance become really important questions.
For sure. Digital art, design, marketing, people are using these tools professionally.
And the images have real value, so protecting them makes sense. The standard approach, or at least a common one, has been to fiddle with the starting point.
You mean the initial noise, that sort of static the diffusion model starts from?
Exactly. Methods like tree ring embed their pattern, like literally these ring patterns, into that initial latent noise.
Okay. And the idea is that pattern gets woven into the final image as it's generated.
Yeah. And it's clever because it often survives things like JPEG compression or minor edits pretty well.
Yeah.
But it doesn't add a ton of computational overhead during generation itself.
Right. So you inject this signature right at the very beginning, before the AI even starts interpreting the text prompt. But as we said, the paper points out a major flaw there.
Oh, definitely. The core issue is that messing with that initial noise, even subtly, changes its underlying statistical distribution.
Okay.
Think of it like slightly changing the starting position in a complex physics simulation. A tiny nudge early on can lead to a completely different final state.
Right. So in the diffusion model context,
That initial distributional shift makes the whole denoising process, the step-by-step generation, drift away from the path it would have taken without the watermark.
and that's the semantic drift.
Yeah.
The image might look vaguely like the prompt requested, but the details, the style, the feeling, it's off.
Precisely. The nuances get lost. And if you're an artist trying to realize a specific vision, that's just not acceptable. The fidelity to the intent is crucial.
Yeah, you end up with a technically watermarked image, but it's not really the image you wanted to create.
Exactly.
And the paper mentions some earlier attempts tried to fix this, like maybe optimizing that initial watermarked noise.
They did. People tried to tweak that starting noise to minimize the drift. But the limitation, as the PTMark authors point out, was that those methods only focused on that initial step.
Ah, I see. They weren't considering the whole sequence.
Right. They didn't account for how the text prompt guides the entire generation process, step by step. It's not just about the start, it's about the journey.
Okay, so that's the gap PTMark tries to fill. How do they approach it differently?
Fundamentally differently. Instead of just fixing the start, PTMark monitors and guides the whole diffusion denoising process. The core concept is quite neat, actually.
Go on.
They leverage 2 trajectories. One is the path the generation would have taken to create a clean, unwatermarked image. That's their guide for semantic accuracy.
Okay, the ideal look.
And the second is the path the generation would take if a standard watermark, like tree ring, was embedded in the usual way. That's their guide for the watermark itself.
So like one path for make it look right and one path for make sure the watermark is there.
You got it. And PTMark then tries to steer the actual generation process to stay aligned with both of these guides simultaneously.
Steering. How does that work technically? The paper mentioned unconditional text embeddings. What's that about?
Yeah, they use the text embedding system that's part of the diffusion model. Specifically, they focus on the embedding that corresponds to no text prompt, the null text, or unconditional embedding.
The blank prompt.
Essentially, yes. By carefully adjusting this embedding at each step, they can subtly influence the direction the denoising takes, nudging it towards that sweet spot between semantic fidelity and watermark presence.
Interesting. So they're tweaking the instructions, not just the image data directly.
Kind of, yeah. It's a clever way to guide it. And this whole process has 2 main stages. First, pivotal trajectory generation, and second, semantic-aware pivotal tuning.
Okay, let's break down that first one. Pivotal trajectory generation. What's the goal there?
The goal here is basically setting up those reference points, those two guide paths we just talked about. They need to know what the clean generation looks like step by step, and what the standard watermark generation looks like.
How do they get the clean path?
They use DDIM inversion. DDIM stands for Denoising Diffusion Implicit Models. It's a technique that lets you, more or less, run the diffusion process in reverse.
So take a final image and work backwards to the noise it came from.
Exactly. They take a clean image generated from the prompt, invert it using DDIM, and that reconstructs the sequence of latent states, the noisy intermediate images that led to it. That's their original or semantic pivotal trajectory.
Got it. Like rewinding the generation process.
Yeah.
And the watermarked guide path.
For that, they take the initial noise they recovered from the DDIM inversion, embed the target watermark into that noise, using a standard method like tree rings ring pattern, for instance.
Okay.
Then they just run the normal forward diffusion process from that watermark starting noise. That gives them the sequence of latent states for a typically watermark image.
Right. So now they have these two parallel sets of steps. One clean, one watermarked. What's next? How do they use them?
This is where it gets smart. At each corresponding time step in these two trajectories, they compare the latent states.
The noisy image representations at that step.
Correct. And they use a pre-trained segmentation network, an AI model, that's good at identifying different regions or objects in an image.
Okay.
They use this network to figure out which spatial regions in the latent state are most affected by the watermark. Where does the watermark pattern cause the biggest difference between the clean and watermark trajectories?
Ah, so they're identifying the watermark zones in the image at each step.
Precisely. This comparison generates what they call a spatial prior mask. It basically highlights the areas where the watermark signal is strongest at that particular stage of generation.
And that mask becomes important later.
Critically important. It guides the next stage, helping the system know where to prioritize preserving the watermark and where to prioritize preserving the original semantics.
Makes sense. Pinpoint the watermark's location. Okay, phase 2 then.
Yeah.
Semantic-aware pivotal tuning. This sounds like the main event.
It really is. This is where they actually generate the final PT mark watermarked image. They introduce a third trajectory, the PT mark trajectory.
Okay.
And the goal here was to optimize that null text embedding we talked about earlier, the blank prompt, so that this PT mark trajectory aligns semantically with the clean trajectory while preserving the watermark information from the watermark trajectory.
Wow, okay. How does optimizing a blank prompt achieve that?
They drew inspiration from something called null text inversion, or NTI, which people have used for editing images with diffusion models.
Right, like changing an object by tweaking the prompt.
Sort of. But here they're adapting it for watermarking. This null text embedding becomes learnable. It takes the actual text prompt embedding as input, and at each diffusion step, it outputs a small steering vector.
A nudge.
A nudge, exactly. This vector gets added to the latent state in the PT mark trajectory, subtly pushing it in the desired direction.
And what is that desired direction? You mentioned 2 goals.
Yes, 2 learning objectives guide the optimization of this null text embedding.
Okay, lay them on us.
First, semantic maintenance. The goal is to minimize the difference between the PT mark latent state and the original clean latent state, but only in the regions outside the watermark zones identified by that spatial mask.
Ah, so use the mask. Keep the non-watermarked areas looking like the original.
Exactly. The loss function for this, L sub semantic sub, essentially measures how different those regions are. Keep that difference small.
Okay, makes sense. Goal 1. Preserve semantics where the watermark isn't. What's goal 2?
Goal 2. Watermark preservation. Here, they focus inside those watermark zones, again using the mask. They want to make the PT mark latent state in these regions align closely with the corresponding latent state from the standard watermark trajectory.
So inside the mask, make it look like the watermarked version. Outside the mask, make it look like the clean version.
That's the core idea. The loss function L sub watermark sub enforces this alignment within the masked regions.
That's actually really elegant, trying to disentangle the 2 signals spatially.
It is. And the overall loss function, L, is just a weighted sum of these 2. L is sub 1, sub semantic, sub plus sub watermark sub. The lambdas are weights you can tune to balance how much you prioritize image quality versus watermark strength.
Okay. And they optimize the null text embedding to minimize this combined loss.
Yes, iteratively, at each time step of the diffusion process, they essentially fine-tune the guidance from the null text embedding step by step to achieve this balance.
Fascinating. So after all that complex generation, how do you actually check if an image has a PT Mark watermark? Do you need a special detector?
That's another advantage. No, you don't. PP-Mark uses the exact same verification procedure as methods like tree ring.
Oh, really?
You take the image you want to test, run it through DDIM inversion to get back the estimated initial noise.
Just like generating the trajectories earlier.
Exactly. And then you analyze that recovered noise, usually in the Fourier domain looking at frequency patterns, and perform a statistical test to see if the expected watermark pattern is present.
So it just plugs into existing verification pipelines.
Yep. It's purely a modification of the generation process. It doesn't touch the underlying diffusion model weights, and it doesn't require any detection method. That plug-and-play aspect is pretty huge for practicality.
Definitely sounds useful. Okay, let's talk validation. The paper must have run a bunch of experiments. What data sets did they use?
They use standard large-scale data sets, MSQOCO set, which is full of diverse real-world images and captions.
Right, common benchmark.
And also Diffusion DB, which is specifically a collection of images generated by diffusion models, in this case, Stable Diffusion. So good mix.
And who were they comparing against? What were the baselines?
A whole suite of them. They included older frequency-based methods like DWTD take, JAN-based methods like Rivigan and StegaStamp, and importantly, other state-of-the-art diffusion-based watermarking techniques.
Like tree ring?
Yes. Tree ring plus Robin and Zodiac, basically the main competitors in this diffusion watermarking space.
Okay, comprehensive comparison. And the metrics. How did they measure success? Both for image quality and watermark survival.
For image quality or semantic maintenance, they use standard stuff, PSNR, SM, higher is better for those, and crucially, also perceptual metrics, FID and LPIPS.
Ah, those try to measure how similar images look to a human, right? Lower is better there.
Exactly. Lower FID and LPIPS mean the watermarked image looks more like the original. Then for watermark robustness, they measured the detection accuracy using AUC, area under the curve, after hitting the images with the various attacks.
Attacks like?
Real-world stuff, JPEG compression, cropping, adding blur or noise, changing brightness, rotation, the kinds of things images go through online. And AUC near 1 means the watermark is reliably detected even after these attacks.
Got it. So the million-dollar question, how did PT Mark actually do? What did the results show?
The results were pretty strong, looking at their Table 1. For semantic preservation, PT Mark consistently beat the other diffusion methods, like tree ring, Robin, and Zodiac, across all metrics.
By how much?
Significantly. For example, compared to tree ring, they reported over 20% improvement in PSNR and SSIM on both datasets.
20% is a lot in image quality metrics.
It is. And perhaps more tellingly, the perceptual metrics, FID and LPIPS, also showed major improvements. This suggests the PT Mark images don't just score better numerically, they actually look much closer to the originals.
That's the key, really. Did they have to trade off robustness for that quality? Was the watermark weaker?
That's what you might expect, but no. PT Mark showed remarkable robustness. It achieved an average AUC of 0.99 across all those different attacks.
0.99, that's near perfect detection.
Pretty much. While methods like tree ring and Robin saw noticeable drops in AUC under certain attacks, especially things like rotation or noise addition, PT Mark held up extremely well.
Better quality and top-tier robustness. Sounds like the best of both worlds. What about speed? You mentioned efficiency earlier.
Right. Table 2 covers efficiency. First, PT Mark requires no model training, unlike Robin, which does. That's a plus.
Right.
And when comparing inference time, the time to actually generate one watermark image, PT Mark was about 4 times faster than Zodiac.
4 times faster than Zodiac. How about tree ring? Is it faster than tree ring?
Tree ring itself is very fast at inference, probably faster than PT Mark's generation time alone. But PT Mark offers a much better balance. You get massively better image quality than tree ring for a reasonable generation time, and it's much faster than other high-quality methods like Zodiac.
So a strong trade-off point between speed, quality, and robustness.
Exactly what they argue.
They also included pictures, right? Visual comparisons. What did those show?
Yes, figure 2. And honestly, the pictures really sell it. You can see side-by-side comparisons. For natural scenes, PT Mark keeps the details sharp and the colors looking normal.
Whereas the others?
Zodiac sometimes had color shifts. Tree ring could introduce blur or artifacts. In drawings or artistic styles, PT Mark maintained the texture and color consistency much better than, say, tree ring, which often looked quite degraded. There was a portrait example, too, where PT Mark really nailed the details and style, while others blurred things, changed colors, or even seemed to lose parts of the image subject.
So visually indistinguishable from the original, as they claim.
Based on the examples they showed, It's certainly much, much closer than the baselines. The difference is often quite stark.
Okay. Now, good research often includes ablation studies, right? Taking parts of their method away to see what difference they make. Did they do that?
They did, yes. Section 4.4. They specifically looked at the impact of their two main components, the semantic alignment objective and the watermark preservation objective.
What did they find?
Well, Table 3 shows it clearly. If you just do basic watermark embedding like tree ring, quality tanks, if you only use their semantic pivotal tuning part, focused on alignment with a clean image, the quality gets much better. But the watermark becomes less robust, it's easier to break.
Ah, so you need both parts.
Exactly. It's the combination optimizing for both semantic alignment and watermark preservation, using that mask that gives PTMark its blend of high quality and strong robustness. You need both lost terms.
That makes sense. Did they test any other parameters, like how much optimization they do?
Yeah, they looked at the number of optimization iterations for that null text embedding at each step. Figures 3 and 4 show this.
What's the trade-off there?
More iterations generally led to better image quality metrics, up to a point. But if they did too many, like 15 or 20, the robustness against attacks started to decrease slightly.
Overfitting.
Potentially overfitting to the clean trajectory, yeah. Making the watermark signal a bit too subtle or brittle. They found around 10 iterations was the sweet spot, balancing quality and robustness.
Okay. And one more thing they tested was when to start this tuning process.
Right, the starting step, sub. Figure 5 shows this. They found that starting the pivotal tuning right from the beginning of the diffusion process, sub equals 0, gave the best results for preserving the original semantics and fine details.
And if they started later...
If they waited and started the tuning later in the generation process, the semantic quality degraded. It seems guiding the process early on is important for maintaining fidelity.
So lots of careful tuning and validation went into this.
Definitely seems like a thorough piece of work. The ablations really help confirm that their proposed components are doing what they claim.
Okay, let's try and wrap this up then. What are the main takeaways from this deep dive into PTMark?
I think the biggest takeaway is that PTMark offers a really promising solution to that core conflict in diffusion watermarking. Quality versus robustness. It shows you can embed strong, invisible watermarks without drastically hurting the visual quality or semantic meaning.
By using that clever pivotal tuning approach.
Exactly. Guiding the generation using both clean and watermarked trajectories as references, steered by that optimized null text embedding and guided by the spatial mask. The result seems to be significantly better semantic preservation. That 10% figure, maybe more like 20% on PSNR Sim, plus high robustness.
And decent efficiency, being 4 times faster than Zodiac.
Right. And that plug-and-play verification is a big practical win, too.
So, for the folks watching, AI researchers, ML engineers, why is this particularly relevant? Why should they care?
Well, if you're building or deploying generative models, especially for creative or commercial purposes, ensuring content integrity and protecting IP is becoming crucial. PTMark presents a practical method that seems to achieve this without the major quality trade-offs we've seen before.
Especially for digital art, filmmaking, design, anywhere fidelity matter.
Absolutely. It potentially lowers the barrier to adopting watermarking because the quality hit is so much smaller.
Definitely food for thought. So, final provocative question then. Looking ahead, with AI generation evolving so fast, how might techniques like PTMark shape the future? What kind of landscape are we looking at for digital content, copyright, and provenance?
That's the big picture, isn't it? If robust, invisible watermarking becomes standard, it could fundamentally change trust online. Maybe easier authentication of AI-generated art, clearer rights management, but it also inevitably leads to an arms race, right? People will work on detecting and removing these watermarks too.
The cat and mouse game continues.
Always. But methods like PTMark push the state-of-the-art forward, making trustworthy AI generation more feasible. It also raises questions about how transparent watermarking should be. Invisible is good for aesthetics, but maybe sometimes you want it to be obvious. Lots to consider.
Indeed. Well, we've only scratched the surface here, especially on the implementation details. If PTMark has piqued your interest, definitely go read the full paper.
For sure. Explore the code if it's available. Think about how it might adapt to different models or watermark types.
And let us know your thoughts. Drop your questions and insights in the comments below. What part of this research stood out to you? Thanks for joining us for this deep dive on AI Paper Podcasts.
Thanks, everyone.